All right. So we're going to talk or move on to something called Meltdown and Spectre, which are computer architecture security vulnerabilities. What that means is because of the architecture of our machines, certain security elements are now possible. These slides were taken from Mark Hill, who's at the University of Wisconsin-Madison when he was working at Google. So Meltdown and Spectre are vulnerabilities that allow a non-privileged user, aka a person who's just using the machine, to read any information on the machine. So that would be like you get on a machine, you hit Meltdown, and all of a sudden you have all the secret keys on that machine. So they present Meltdown Spectre or have multiple issues. In order to accomplish this, there's two things that they had to take advantage of. One was out of order CPU. We haven't talked about this, but excuse me. Hopefully the problem here at least starts to manifest itself inside of in order. What's happening even in order is that if there's a branch misprediction, some instructions begin to execute after the branch. Now in order, it's able to squash it before anything happens, but in an out of order machine, some of those instructions may actually complete before the branch misprediction occurs, and then the processor has to fix it. And that's going to be very important for Meltdown and Spectre. Another one is how caching brings in multiple bytes. So we talked about caching and how the cache line was brought into memory. We're going to focus on Meltdown because it's way easier to understand, and then I'm going to talk a little high level about Spectre because it's very similar to Meltdown, but it's way more complicated to implement. Alright, little architecture. Remember that we have a microarchitecture, which means that the architecture of your machine looks like it's just executing instructions, but the microarchitecture may be doing something a little different in order to complete that. Alright, talks a little outline, so that's great. So pre-1964, you had hardware, not much software. So 1.0, they talked to instruction set, so you could program in assembly. And then Moore's Law, talking about transistor count. And then we talked about, now we're going to move on to Meltdown. I know that was a brief overview of the history, but let's go ahead and move on to Meltdown. The first step of both Meltdown and Spectre is to copy any unauthorized information into our cache. Alright, what are we talking about here? Remember, when you copy memory from main memory into cache, it's doing the entire cache line, which may accidentally be bringing in other data. But also, inside of an out-of-order execution, if you have a branch, and then, well, we'll talk about this in a little more detail, but the first step is to get the memory into cache, and there's some tricks in order to do that. Once it's in the memory, we need to come up with a way in order to read it from the cache line. Now, normally, if you read a piece of, or you have a piece of data you're not authorized to have inside the cache, there are protection bits inside the cache in order to prevent you from directly reading it. So we need to come up with a way to indirectly read that memory. Alright, to get it into memory, we're going to take advantage of speculative execution. Now this is to, first step, copy unauthorized information to the cache. So we're going to execute instructions that should be squashed after a branch, but has the side effect of loading the unauthorized information into our cache. In other words, we're going to have a branch, and then the immediate instruction after that is to load a piece of memory that we're not authorized to have. And so it's going to mess up on the branch, but this load's going to occur first and actually bring it in. So real quick, speculative execution, you might have add, load, branch, and store, predict the direction for fall through. Alright, I think this makes way more sense when we have the assembly. We talked a little bit about this pipeline, so let's do it. Remember, you have instruction fetch. This normally in our in order is execute and then memory. In an out of order machine, this is done very differently. Things may be executing in different orders, and then will all be reassembled over here in memory. So it may talk about this, where detach, decode, reallocate, and then it's allocated into execute in any order. This reorder buffer, we don't have time to go through all this, but the reorder buffer makes sure that this is all serialized in the in. But the point of this is that if we have a branch, and this happens, go to an error, and then let's load this afterwards. And here's the big difference, or the way, or why meltdown occurs, because if this branch is mispredicted and it's supposed to, you speculate not taken, but it's supposed to be taken, then this load is going to speculate in the load. In other words, it may be trying to execute this branch, but then the load comes here into memory, and it may complete before this branch completes. We can speculate the AND as well, and then speculate the load and speculate a cache hit. Alright, what would happen if the mispredicted branch was not taken and we set the variable train right here, such that the load would be from an unauthorized area? Well, the load would execute, bringing the unauthorized information to the cache. The load would be flagged as segmentation error, because that's what's supposed to be inside of this, because you're not allowed to load from it. But instead of stopping execution, as a fault does, the mispredicted branch squashes the fault and the load and the fault. So in other words, it squashes the load and the AND, but the side effect of bringing that memory into the cache has still occurred. So now we can have a way to bring memory into the cache that we're not supposed to have in the cache, and that was by utilizing the fact that that load or unauthorized load was squashed because of a branch. How do we read it? Well, we can't directly read it because we have hardware schemes that prevent us from reading it. So we're going to create a covert channel by using the cache as a side channel. Alright, these are covert channel and side channel are security terms. So let's see how we can do that. Well, main memory is 1,000 times slower than the cache. So if we're trying to read from the cache, that'll be fast, and we try to read from main memory, that's slow. Alright, cool. So we're going to take advantage of timing. So we use the cache as a side channel to determine which element of data is in the cache. So we're going to take a timing, RDTSC, and then we're going to try and access a piece of memory, and then we're going to ask how long that took. Alright, execution is proportional to whether it's in the cache. In other words, if this piece of data is in the cache, then this number is very low, and if this piece of data is not in the cache, this delta 2 is going to be very high. Alright. So how do we do this? Well, we have a speculative execution. Again, we're going to take advantage of the fact that this needs to be programmed to be mis-executed or mispredicted. So it's going to access or do these lines of code before it realizes it's wrong, and then it'll jump out. So if it's mispredicted, but before that memory at pointer was in the cache, aka this guy was in the cache, notice what's happening. We try and read from this, it was in the cache, so this happens quickly, and then unsigned log index 2, we're going to, well, this is kind of confusing, get the value downshifted by a bit, ANDed by 1, multiplied by 100 plus 200. Wow, that's confusing. And then we're going to try and access the data. Okay. Both memory 200 are not in the cache. After squashing the branch, would data 200 or 300 be in the cache? Well, that's a good question. So, did I not write down how to do this? When the right condition exists, the branch of the code will run speculatively, the privilege check value will fail, and the access will occur, although value will be discarded when the speculation is undone. So the offset of accessing the data is dependent on the value of the privileged data. In other words, this we have access to. We are allowed to know if that value is there. Since this is executing speculatively, this will be read in, and index 2, we basically are reading 1 bit from this pointer and storing a 1 if it's in there and a 0 if it's not, and then writing it to a piece of memory that we do have access to. This is normally not allowed, but since it's speculative execution, these accesses are going to be executed and they're going to complete, but then the violation right here will be squashed because of the architecture. Notice this value is 1 if it's in the cache, because this whole thing is going to execute very quickly. This value is going to be 0, or the previous value, if it's not in the cache, because by the time this completes, it's going to be squashed. So, this means that this piece of data, if run enough, can read 1 bit at a time from the cache. Let's see. So we talked a little more details there. A little more there. Hopefully some of y'all know about this. This was a fun little, at least game on NES, but this is Spy versus Spy. This goes back to the Orange Book of the DoD, which hopefully, well, y'all probably haven't read that yet, but is a very popular book for computer security. So what Meltdown does, and they talk about how to do this in memory, basically where there's a trap and misspeculation, just like we talked about before. But the idea is that it can read secret keys inside of your machine. So it's been demonstrated on x86 hardware. It is not demonstrated on AMD, so older versions of Intel do fail. Why? Well, what happens is, or why does this work on Intel but not on AMD? It's luck. AMD's microarchitecture just happens to not be vulnerable to this, while Intel's is vulnerable to this. That sometimes happens. So in this case, AMD lucked out, and they did not have a problem with this meltdown. Intel has come up with schemes, or they have fixed their microarchitecture for new chips. The bad news here is Meltdown operates with bug-free OS software. By the way, while I say their new chips don't have vulnerability, that means all their old ones do. And that still comprises a lot of machines out there, so a lot of machines are vulnerable to this. Luckily, a lot of machines were patched in 2018. They use something called Kaiser, but there is up to a 30% performance impact. And this is very common and a huge problem in security. Is every time you inject a way to mitigate a vulnerability, your performance decreases substantially. But AMD doesn't suffer from this, so AMD is kind of rocking it right now. Alright, we're going to switch over to Spectre. Spectre is going to utilize that second phase, phase 2, where it was able to use a side channel to read something into the cache. But phase 1 of reading something unauthorized in the cache is going to work differently, because the first one is, well, the first phase of reading into the cache is how Meltdown worked, and the second one's going to be how Spectre works. And we're going to do a high level view because it's actually very complicated to get Spectre to work. It loads up the branch mispredicted, but it loads a misspeculated using an existing library code. So this is why it's hard, because you have to know what library code, aka the exact version of the operating system and the exact version of all the DLLs or SOs that are loaded on the machine. And it's going to be able to pick a certain branch in that library code that is susceptible to this vulnerability. And so it's going to read it into memory. Let's see if we have any more. And then it's going to exploit, again, indirect branches as a side channel. They did show that JavaScript running under the Chrome browser could be used for this vulnerability. They demonstrated on Haswell, as well as AMD and ARM. Basically, any out-of-order processor is vulnerable to Spectre, and this is not something that has been mitigated. It is just a vulnerability that exists. There are some, actually I should say there are some mitigations out there, but for general, it's just accepted that this problem is out there. And the reason why most people are not concerned is while there's a high risk here, the chances of someone pulling this off is incredibly low. Because they have to know exact software that you're running on your machine. And also, there are ways, and one very good way to mitigate this is every time you boot your software, you randomize a lot of the branches in your library code, and then that makes this even harder to take advantage of. So Spectre is basically a known vulnerability that people just make hard for hackers to take advantage of. Alright, that's what I just talked about. So now they're talking about, do we need another version of architecture? Well, we'll see. But it can be very difficult because speculation improves performance greatly, and if you drop speculation, basically our processors go back to the early 90s and late 80s. Alright, so that's Spectre and Meltdown I've run through there. This was another example for your presentation. I know a lot of y'all have been selecting them. If you've not selected one, please email me or go on Discord. Really, Discord's a lot better. And message me either through computer architecture or directly for what you want. I have on Discord listed what is left and what is available. Do not present on something you haven't told me. Your grade will be a 0. Alright, that is all for today. There is no homework. We'll resume a couple more topics next week, but today this was very important to see why caching is so important for performance and cause problems with security.